Hello everyone, my name is Zhen Lin. The paper I will be presenting today is titled with General Purpose Deep Tracking Platform, across protocols for the Internet of Things. This is a joint work with my colleague Dr. Qiong Zheng, Dr. Ping Li, and my supervisor Dr. Lei Yang. We are from the Hong Kong Polytech University. Today, IoT is everywhere around us, such as the Zigbee, RFID, MBLT, and LoRa. They make our life more convenient. The IoT increases rapidly. As reported, there will be 21.5 billion IoT connected devices by year 2025. The IoT family also diversifies quickly. There are numerous IoT technologies invented. This work focuses on the localization service in IoT. Our vision is that there are complex wireless localization demanding in our daily life. Considering we have a modern factory, if we can localize the IoT beacons, we can use them to track the people so that they can cooperate better. We can also use RFID tags to monitor the items on the carry belt and take the inventory of the goods shelf. If we can get the accuracy position information, it will be convenient for us to find the missing object. Also, if we can localize the Zigbee node, we can deploy them to the robot for indoor navigation. To achieve this vision, many wireless localization systems are invented. They can be classified into 3 categories. The first one is the fingerprint, which has been widely used in Wi-Fi, Zigbee, and the RFID. Also, there are many classical models, such as the TOF and AOA. Recently, there are many machine learning-based localization systems invented for the robust performance in complex environment. However, all these classical methods require the receiver cooperate with the transmitter, because the way they measure the position is based on the stable connection with the devices. When we need to deal with hundreds of devices, many times are wasted for building new connections between different devices. So we need a non-intrusive system. Another problem is that the classical system required a specific receiver, which means if we want to localize a Zigbee node, we have to deploy 3 or more Zigbee receivers for a 3D localization. It is inconvenient for us when we deal with different protocols. Also, all systems require the regular calibration. If each protocol has its own localization system, it is a huge cost for us when there are many different localization systems. So we hope to have a system which can work for different protocols and can do this job all in one. In conclusion, we need a non-intrusive general purpose localization platform. So we propose iArc. It is a new localization platform, which is non-intrusive, which means we do not need a cooperation from the transmitter. Also, it is compatible with different protocols. Also, it can work high precisely in a complex environment. The core of iArc is a large antenna array, which can sniff the wireless packets on the air. It is a planar array with 64 elements. Such huge antenna array size can be the foundation for the high accuracy. To save the cost of RF chain, we design it in a switch model. For each time, we only connect one antenna element with the RF chain. And the switching operation is implemented with the RF switch and the FPGA to decrease the delay. We can switch it with only microsecond level delay and localize a device with only a glance, which means we only need one packet for the whole 64 antenna measurement. However, it is still difficult for us to make the system general purpose because of the protocol diversity. In traditional wireless system, different protocol pick different modulation techniques. For each modulation, we have to demodulate and then measure the channel. Even though we can solve the modulation problem, we still need to cope with the channel diversity because different devices works on different channels and they also keep hopping. If we focus on one channel, there will be huge carrier frequency offset for the other packets on the other channels. And we need to calibrate the frequency offset. The traditional solution for this problem is using a long preamble or training sequence to do the calibration, such as the FFT-based calibration. The longer of preamble, the better calibration. However, it cannot work for fast switch antenna array because each element can only collect a slice of packet or a slice of a symbol. It is impossible to use the traditional solution. So the problem here is how can we measure the wireless channel with only a fragment? Another challenge is the complex environment. In complex environment, the signal will go through many paths. And the multipath signal will impact the localization. Although we have the antenna array, we can use the naive finding to separate them on the spectrum, a spatial spectrum. But for sometimes, the naive finding may confuse us. Here is an example. If we do the naive correlation on the spatial spectrum, we will find the peak point at the red point. And the white point is the ground truth. You will see the gap between these 2 points. This distraction is because the coherence of multipath signal interferes each other, and the naive method cannot decompose them perfectly. So the problem here is how can we find the real direction? So to solve these problems, IARC consists of a protocol-free channel estimation model and a deep tracking network. The first model is for the general purpose measurement. The second model is for better localization performance in complex environment. Let me introduce the protocol-free channel estimation first. Imagine there is a wireless packet which may be modulated with amplitude, frequency, and phase. The wireless packet will go through a wireless channel, H1, arrive at the antenna array, and we will receive the signal like this. In traditional solution, we need to first calculate the amplitude, frequency, and phase offset, and remove them all. And we need to do this calculation on a long sequence to ensure the accuracy. The idea of IARC is to utilize another antenna to help us do this calibration with only one sample. Considering we have another antenna, the signal will go through another channel H0 and collected by the antenna. And we will receive the signal like this. We call this antenna as a side channel and the main channel for the antenna array. If we divide the signal from the main channel by the signal from the side channel like this, you will see that the amplitude, frequency, and the phase offset are naturally removed. So we can do this to get the relative channel state information and use this for localization. Next is about deep tracking networks for the robust performance. As we discussed before, the multipath will worsen the spatial spectrum. This is because the line of sight signal will align with the coherent multipath signal, make the max point of the spatial spectrum away from the ground truth. So we improve this by using the deep convolution network. The core idea of this method is to decompose the signal by spatial smoothing. We train a deep convolution network to improve the AOA result and use a fully connected network to combine the result from each subarray and output the final position. In such way, we can improve the accuracy and make it robust in complex environment. Next, let me introduce the dataset and the evaluation. The ground truth of dataset is collected by an OptiTrack motion capture system, which can provide the sub-centimeter positioning accuracy. The dataset is collected in a 200 square meter office. It contains 270,000 samples over 5 popular IoT protocols, the LoRa, Zigbee, NB-IoT, RFID, and Sigfox. The first question is about how good we can find the direction. We do this evaluation on an 8x8 antenna array. The green line is the result from the traditional solution. The red line and the blue line is the result from IARC. As you can see that the median indoor AOA accuracy is only 0.46 degrees. As far as we know, this is the best record for the indoor localization at the UHF band. And the result from the traditional method is only around 1 degree. The reason for this improvement is about our AOA network. It can decompose the multipath interface, even for some difficult scenario. Next question is about how good we can find the position. We do this evaluation on 3 dimensions. As you can see that we did a great job on Y dimension, but performed bad on Z dimension. This is because we only use 1 planar array. The Z dimension change for a planar array is not that obvious like the change on Y dimension. But this can be much improved by deploying another antenna array on the ceiling. For the accuracy on Y dimension, our media accuracy is around 3.9 centimeters. This is much enough for most daily use. Finally, is about how can we handle with various protocols. We evaluate with 5 popular IoT protocols: the NB-IoT, LoRa, RFID, Zigbee, and Sigfox. As you can see that the accuracy over these 5 protocols are very similar. No matter how they modulate the packet, how they pick the channel. This proves that IARC is compatible with popular IoT protocols. In conclusion, IARC is a new localization platform which is non-intrusive and compatible with different protocols. Also, it is a high precise localization system, even work in complex environment. Thanks.